Welcome, everyone. It's a great pleasure, yes. Change identities, that helps. Wonderful. It's a great pleasure to welcome everyone to this last inaugural lecture in the year of 2022. The year is coming to a close, a very special year, I think, for all of us, with all its challenges, but also with all of its successes for our university. I think we can all be really proud of what we have achieved. And now we have this wonderful occasion tonight. I'm greeting particularly our guest of honor, Sabine Roller, and we came for you, and we are very pleased that you came for us. And let me tell you a little bit. So we have started this new format, and I think it has been a very interesting series of inaugural lectures that we have listened to, and you can still listen to them. They are in our YouTube channel. I think they are characterized by the following two things. The first one is that all of the inaugural lectures that we selected to represent either new colleagues from the excellence clusters or new colleagues that represent research priority areas of our university. But they are also characterized by bringing together different disciplines, by a deep embracing of interdisciplinarity. That's the first. The second one, I think they were all characterized, or across the year, we made sure that we represented another cooperative feature in Dresden, and that is that TU Dresden has this wonderful opportunity to be in the middle of a rich array of research institutions outside of the state universities. And so we have had a number of colleagues who we jointly appointed with either a Fraunhofer Institute or a Max Planck Institute. And tonight it's together with another important partner of us, the German Aerospace Center. And so it's these two cooperative spirits, one between disciplines and one between research institutions, that I think is like a red thread through these inaugural lectures this year, and I think it will carry on next year as well. I'm also extremely pleased to welcome another female leader in our community, and in particular as it is in a discipline that is not overcrowded with female leaders. So we're very, very proud about that as well. And so we are welcoming the new director of the Institute of Software Methods for Product Virtualization, which is part of the German Aerospace Center. And it is one more important project, this joint appointment that we share with the German Aerospace Center. We are running the supercomputer Kara, and we are indeed the high performance computing center for the German Aerospace Center. And we, with welcoming Sabine Roller to our campus, we bring a professor of exceptional excellence for the Institute of Artificial Intelligence, which is part of our computer science faculty, and a director at the Institute of the DLR. Sabine Roller has been combining in her very successful career always basic and applied research, which also fits very well with many of our areas of activity at TU Dresden. And in particular, her goal is to come up with a digital description of an aircraft with all its properties and components based on highly accurate physical and mathematical models. And it goes without saying that in the degree to which she accomplishes this goal or gets closer to it, of course, the possibilities of application in other fields are numerous. I don't want to say endless, but numerous. And so I will not tell you about the details of her career because we have two speakers after me and they will do that. But I would like to join me in giving a hand to welcoming Sabine Roller as a new member of the TU Dresden community and as a member of the Dresden Concept Science and Innovation Campus. Welcome very much, Sabine Roller. So as you know, what's going to happen next is that we have two representatives, one from a very important, of course, the joint appointment has to be between an outside research institution and a faculty of our university, and that is the Faculty of Computer Science, and so it's Ivo Spalzarini, the dean of this faculty, who will speak, and then there will be Wolfgang Nagel, who is Mr. Data. So we have seen you in our new Excellence movie, and everyone said afterwards, we always knew that you are dealing with these square, upright rectangles, and that's how you do it, how you're spending your days. Anyway, so Wolfgang Nagel will be speaking to us about the linkages and the cooperation with our new Center of Interdisciplinary Digital Science at TU Dresden. Before I hand over, I'd like to thank, as always, the team behind the scenes, without whom this would not be possible here. We have our colleagues who are making sure that the stream is going well and that will be uploaded afterwards. We have Silvia Kaplusch from the Faculty of Computer Science, who has helped greatly to bring it about. And to start everything, it's Christine Milkau from the protocol. And we have from the DLR Center, Anja Hennig, who has been helping. And after the presentation by Professor Roller, we have a Q&A, but then we have a extended Q&A downstairs over a glass of champagne, if you like, and you can continue your conversations with our new member. And without much further ado, I'm handing over to Ivo. Please, Ivo, it's your turn.
Thank you, Ursula. Big welcome also from my side. I'm happy to see so many of you here, and I'm happy to be the one to speak between the rector and Mr. Data to open this inaugural lecture. Magnificentia, dear Ursula, dear Sabine, first and foremost, dear members of the extended rectorate, dear fellow deans, dear members of the Faculty of Computer Science, dear students, dear guests. As has been said in the introduction, I'm Ivo Spalzarini. I'm the current dean of the Faculty of Computer Science, and tonight is one of the opportunities where it's actually a pleasure to fill this role. I'm very happy to introduce Sabine Roller on her inaugural lecture, university-wide inaugural lecture, which I think is a fantastic format. Sabine Roller has been a professor for software methods or software technology for product virtualization since the beginning of February 2021. And as our rector has said, she is at the same time the director of the DLR Institute for Software Methods for Product Virtualization. Her work on programming models and data models for high-performance computing, but also simulation frameworks, platforms and environments, as well as methods for data analytics and surrogate modeling, does not only perfectly fit the research focus and strategic development of our faculty, but enriches it in an area that we have not had so far. And this also has been said initially, is the interdisciplinary applications that Sabine Roller brings in the area of aeronautics, which traditionally in the history of computing, all the way back to the 1960s at Caltech, has been one of the core application areas for computer science, and amazingly was something that we did not have here until 2 years ago. This application that Sabine Roller brings new shows once again how generic and universally applicable the tools and methods of computer science are in the sciences and in engineering and beyond. But it does not only bring a new application of strategic importance to our faculty, Sabine also brings a new institutional partner of equal strategic importance, because it's the first joint appointment between our department and the German Aerospace DLR. And the importance is indeed strategic, also as the rector has mentioned initially. The Dresden concept that we all love so much gains a new member with the DLR's, at least so far, first institute in Dresden. And this collaboration is already bearing fruit. I just want to highlight the example of the DLR School Lab collaboration between the Dresden Concept partners, which introduces kits to topics of energy and future mobility with an exhibition at the Technische Sammlungen, and hopefully motivates many of them to enroll in STEM subjects for their studies later on in our university. And Professor Roller is also managing the high-performance computing infrastructure for the DLR, which, as we know, has already moved to Dresden and serves the Republic from here. And this strengthens also our visibility and our position on the European map of high-performance computing as one of the leading places. The synergies, therefore, between the DLR and the Faculty of Computer Science are obvious, be it in the Computational Modeling and Simulation Master's Program, where we can extend the teaching towards computational engineering, computational aeronautics, and virtual prototypes, or be it in using this interdisciplinary topic to bring us closer together with our partner faculties within the School of Engineering Sciences. In this sense, a big, in all capital letters it's written here, big welcome, Sabine, and thank you for everything you have already contributed to our department and to TU Dresden and Dresden as a whole, where I'm sure many more, much more is still to come. And now I'm going to hand over to Mr. Data, my dear friend Wolfgang, who is going to introduce the speaker in more detail.
Magnifizenz, Spektabilität, dear colleague Sabine Roller, liebe Sabine. What should I say? It is clear that you have started very early in your life with what we are doing these days and interpreting by MINT, mathematics, computer science, natural sciences, and technologies. Bring that together and give that message to pupils, small kids, larger kids, even on the level of students. And you have started so. And it's the honor for me now to talk a little bit about your history and what you have done. You have studied technical mathematics at the University of Karlsruhe, and these days KIT, you know. And yes, mathematics was the major. The minor was mechanical engineering. And another minor is applied computer science. So just from the beginning, you have done what we would love to see more girls doing, investing in future in areas which are really interesting. And you can see what is coming out at the end. You made your PhD and defended it at the University of Stuttgart in the Faculty 6, Aerospace Engineering and Geodesy. These were 2 steps which showed the direction. But then there were a couple of other steps in between, which I will mention just shortly, where you showed your broad interest and your contributions into different fields. And I liked very much that you even started as a stipend at the Institute for Neutron Physics and Reactor Technology at the Forschungszentrum Karlsruhe, which also is a kit now, but at that time was one of the large research labs. And maybe you have learned already at that time that sometimes it is good to be in a large organization focused on research. Maybe this has given you the hint where to go in the future. After your activities in the Institute of Aerodynamics, I wouldn't say you ended up, but you moved to the HLRS, which is one of the largest, most powerful supercomputing centers in Germany. Very successful, focused on industry and collaborations, and you learned from the beginning, with your background, what HPC is needing. And actually it is applications. It is not the computing. It is the computing and the modeling, the simulation has to be done, but in principle it is also the application which drives all these method developments, which was very interesting. And that was the time when we met first. I know that you were just across the meeting room, and I went into you at some point. I do not know exactly at what year, but it was in the middle of the 2000s. But it was just a step on your career. I think it is important to highlight that you headed a group of scalable computing and coupled systems together with the Teraflop Workbench cooperation with NEC. So the collaboration with companies bringing expertise together from the field of the simulation and modeling, but also from the real industrial aspects, was at the same path on your ladder. And I was really happy when you made the next step, which was going to my alma mater at that time, in former times, at the RWTH Aachen, where you got a full professorship, but on a limited time position, and also got part of the German Research School for Simulation Sciences together with the Forschungszentrum Jülich, Research Center Jülich. I think a very fruitful time. I have seen the new building which they have installed on the parking spot where I always, at my time, stopped with my car. And it was not the last step, it was just an intermediate step, because then you showed me how things are really done as a computer center head. So you got the head of the computing center at University of Siegen, and also their professorship, which actually was on simulation techniques and scientific computing. It was a full professorship. And I was looking to Siegen a little bit earlier as part of my DFG job, looking to the infrastructure. And I have seen what you have done with University of Siegen, and this was impressive. So thank you for that. instead of being here from University of Siegen, but I think it was really an investment of your time and also a very successful collaboration with all the people there. Yes, and since February 21, you are now with us. And I would say next door. Actually, from out of my office, I think there are 6 meters, and then I'm in your new building. And you take all the light I had. But this is okay. There's always hope that we get a new building, and then I will try to get where nobody can take the light away. So your building is on the way. And I think this is also important that you have a home, and this home is just in the middle of everything where you have collaborations. This is the computer science faculty, but also there's a computer center side by side, and there is the building Lehmann-Zentrum Bürogebäude, which we are waiting for, and which also will be very close in all the activities designed there. I will not talk about the Institute of the DLR. I have had one short paragraph on that, but I think you will explain much more and even in more detail what you are doing. I want to refer to prizes, and you got the Amelia Earhart Fellowship Award. And I'm not sure that everybody knows what that is, but I found out that it was established in 1938 in honor of the famed pilot and Santonian Amelia Earhart. And actually, they are awarding annually up to 30 women worldwide pursuing on PhDs in aerospace engineering and space sciences. And you got it at that time. And actually, it was also awarded by some US amount of dollars, which I'm pretty sure you have good invested into some research activities. But overall, this prize, you are one of 1,704. And this can be a large number, but it is not. It's only 30 per year on a worldwide level, which I find very impressive. Congratulations on that. You also got the Outstanding Teaching Award of the state of Baden-Württemberg, together with 2 men. I couldn't name the names, but it doesn't matter. And I think it was a pretty early stake. You have invested also in teaching. And yes, we know that this is important and it takes time. And it was a significant investment also for you, and you made it on the state level, which I also find it very impressive. So if you look to her career, I think you have been in pretty much half of the TU9 University, which is Karlsruhe, Stuttgart, Aachen, and even Dresden. And we hope that this will have no follow-on. Please stay here. You are currently involved in a couple of committees at DFG level, which is WGI, and pretty much all German people know what it is, but maybe not the English-speaking ones. So it's a Scientific Equipment and Information Technology Committee, which is very important because it looks to investments, big investments in Germany in the university level, and also to the AWBI, so AWBI, the Committee on Scientific Library Services and Information Systems, where you look to data. Not all data, but many projects which are related to data. You also were in the past steering committee member of the priority program 1648, Software for Exascale Computing, and it was a pleasure because I was heading it together with Hans Bungartz from TU Munich. It was always fun to work together with you and seeing you in that important position, because you have steered us pretty well. Thank you very much. Also important is that you have been the vice chair of the strategy committee of the GWK on NHR, the National High Performance Computing Initiative, which has started 2 or 3 years ago. And I think you have moved us a long time us as HPC on the second level to get on the right track. And when you got the position here, it was over, because now we are very close, and therefore you were not allowed to stay longer in that committee. But it was very important to have advisors like you in that committee to bring the whole program on the right track. Now you have different committees, appointment committees. And I think I'm allowed to say that she is also in the selection of the Deutschland stipendium, so be careful. She gives recommendations. Yeah, why I'm standing here and doing that? Well, there are collaborations always since that time of HLRS and also in the German Research School for Simulation Sciences. But we also, and this was mentioned already, we have a collaboration, a very close collaboration between DLR and ZIH. So the operation of CARA, which is a computer for advanced research in aerospace in Dresden, is installed since February 2020. And we have also a strong research collaboration where we look from the performance point of view, and you are looking from the application and method point of view. And overall, I think that we have significant steps forward to improve codes and even reduce energy need with respect to that, because you can improve and make programs faster, which I think is very important. And we are not alone. It is GWDG, so the Göttinger HPC Center, which has joined us in a trilateral cooperation, and I think this is also going very well. So she is not only relying on us as a provider for HPC, also Göttingen is part of that deal, and I think this is important. So whenever we might have a problem, Göttingen will take over, and there was some time where Göttingen was not available, then we were available. And you have been a PI in SCATS-AI. SCATS-AI, I think, is something where we are just starting to get benefits and to earn what we have invested over years. And I'm really happy that you made it just from the beginning, and we are working on a working group which I think we will have within the next 6 months established, where you promised to do something which is beyond my activities these days, which is quantum. And the hope is that your expertise will help me to understand what these guys all want, just to make sure, yes, it will have solutions, but it might take a while, and we will see how this will work. So your focus is always, has been always on HPC. You're coming from applications, but beyond the coupled systems, the coupling of physics as well of machines, and the heterogeneous hardware is driving you, the DLR, and us to make things work, provide solutions. The hope is to have a single software at the end which make all that what you will promise in a couple of seconds. I'm pretty much at the end. I just want to say that this is also a wonderful example where things are coming together. At the point when you were about to be hired, we were looking for somebody who is heading our network group. And we found one, and he came from Siegen. But we were not sure why he was coming. But at the end, it is dual career, without any help. We have looked for the best guy, and we got the best guy. And yes, we got also you. And yes, you are also the best we could get. Last but not least, I think I want to mention 2 things. She not only brought her husband, she also brought her son. which is Roman, and he is now studying computer science at TU Dresden. So the next generation will follow up. And finally, and I have not tried to translate that, she has invested in a Dreiseitenhof in Saxony, and she is renovating it. And actually they are living in that already. And I know how much work this is from other examples. But also this means that you have really arrived in Saxony. And therefore, welcome, Sabine. I'm very happy that you're here, and we are now looking forward to your talk. Thank you very much for coming and giving that lecture.
Thank you very much. So, magnificence, Ursula Staudinger, Electability, Ivo Spalzarini, dear Wolfgang, dear colleagues and guests. I'm very happy to be here at TU Dresden in general, and literally spoken today here in the auditorium, because yesterday I got stuck at an Airbus visit at Toulouse, which brought my time buffer from 1 day time buffer down to 10 minutes. So Anja, I'm very happy to have you assisting me, organizing everything, going from update to bug, from update to bug to all the next issues, but we made it in time. So just-in-time delivery holds even for professors, but interrupted delivery chains are a problem. So I definitely would like to talk about airplanes today, but not on physical ones, which have stressed me quite a lot. But I would like to talk on the virtual aircraft, on the software that contributes, and the methods that are behind the technologies to deliver software which has a high quality. So let me start with a definition. The virtual product, what we mean with it is a digital description of an aircraft with all its properties and components based on highly accurate physical and mathematical models across all the disciplines, in every phase of the development, and across the entire aircraft life cycle. So with that is the lighthouse which we want to achieve, and of course that means that software is everywhere. Software is ubiquitous. It is employed, of course, in the development phase of the aircraft, in the certification, in the production phase, in the deployment phase, maintenance, and overhaul. So we have different areas, different people to use it, different target groups. So we need different methods and different technologies. So we deploy software for simulation, for data storing, and especially data management, for process steering. So I would like to draw the large picture a bit today. What we would like to have is a number of building blocks that we can fetch together to construct environments and tools that assist people in developing the next product. But of course we don't want to plug it together and then put it to the shelf and have a look at it, but it is meant to be a tool that people can use. So we want to have all those gears working together, interacting, and as usual, the devil is in the detail. So obviously, we need a lot of methods, technologies, tools to get all that done. And with that, I would like to give a short outline of today's talk. Of course, it's about aircrafts. That's what we want to get in the end. And I will talk about individual software, multi-software environments, methodologies. So I would like to mention a lot of different things. I would like to draw the large picture, talking about all the individual pieces, but more or less scratching at the surface only, not going down into the detail of any single piece of the puzzle, but touching everything that is necessary to achieve the virtual aircraft in the end. So when talking about individual software, it needs to be good software. It needs to be quality assured, it needs to be efficient, it needs to be effective. So efficiency we'll talk about, that's performance on the machines, but effectiveness also means that it should be suitable for the actual application scenario. So for a lot of areas, we rely on high fidelity methods, which are typically cost intensive, and we have to do that very good. But sometimes it's more important to be fast, and we also need those methods in the loop and in the workflow. And when talking about resources, compute resources for the moment, we have to see what to do with the resources. If we have larger and larger resources, it's a different method to solve the same problem in a shorter time, so considering the strong scaling, or to tackle a larger problem in the same time, what we call the weak scaling. Even for those two questions, it's not exactly the same methods, but we have to have a look at all ends of the system, of the problem. So high performance computing, HPC, is a key component for digitalization in aerospace industry. Wolfgang already mentioned how important it was in my career already and how important it is for the future development in industry. So when looking at the different components, what is needed for developing an aircraft is the physical description. So for example, the fluid dynamics, computational fluid dynamics, which still is the working horse, one of the most important applications that we have on our machines. So we have the institutes working on fluid dynamics, like Jochen Fröhlich here in Dresden. And we are considering the software side, trying to improve the software with respect to the performance. So the first step is to analyze how good or not that good it is. So find out where's the hotspot, work on it. For that, we already use tools like the Vampire tool, which is also developed here in Dresden. And then, of course, we do not just want to know where we have the issues, but of course we also want to optimize it. And for the optimization, we always have to touch the mathematical description. So sometimes we have to improve the math or select the best mathematical method. But we also have, of course, to deal with the computer science technologies, how to bring it to life, how to bring it to good performance. Again, with finding compromises, sometimes like, for example, working with mixed precision. So with that, I would like to mention some highlights, like the hypercoda, coming back to what we are looking for. We are looking for something that is used to develop new aircraft. And that, of course, means the fluid dynamics, as already said. And then from the application comes the need for extensions, like here, extension to hypersonic. So it's the application driving the need. And then we're considering the methods by implementing the best suited methods that we have available on different levels, starting from the very core with the matrices. Typically we have to solve linear equations and we need to have highly scalable linear solvers, like our SPLIS library developed in the institute. I don't want to go too much into the mathematical methods. I want to emphasize on the HPC needs and necessities, like efficient parallelization, working for distributed memory, shared memory applications, but also looking to future hardware. We already had the discussion on the development on the hardware side. So, of course, we are working on the CPUs, which we currently have, on the GPUs. We work on vectorization. As I said, I don't want to go too much into the details, but when looking at, for example, the GPUs, we have to consider different ways. It's not unique, it's not just apply it, it's investigating in different ways. For example, could apply it as the first approach as a combined asynchronous workflow on CPUs and GPUs, or we could apply it with a CUDA-aware MPI on GPUs only. We have to be prepared for machines to come, which will definitely have more and more GPUs. But we, of course, do it also because it gives us something. When looking at the application, we can compare the CPU-only version. We can port it to the GPU, which already gives us something, so the hardware gives us an improvement. But then when we start to optimize it, so when we put brainware in there, we start to think about things and optimize, then we gain even more. But when looking at the applications and the improvements that we get with the optimizations, the most important is make it better suited for the users who want to apply it later on. For them, it's turnaround time. How fast do I get my problem solved? But when looking at the resources, it's not just wall clock time to get to solution, but of course we have to look at the costs, and the cost is not just cost in euro, but you all know the discussions that we have today, it's cost in kilowatt hours, it's energy costs. And for that, we also have to investigate. Of course, the faster, the more efficient the software is, the less energy it uses. But the improvements are different on the different hardware when I just look at the speed up in wall clock time or when I compare it to the energy consumption. But we do not end with the future technologies that are already there and are upcoming, but of course we want to look into the future developments. So as Wolfgang already mentioned, we are looking at quantum computing. So Pia, you know what you have to do when explaining it to Wolfgang. We would like to know, is it just a buzzword? Is it just something that is nice to have? Or is it something to be useful for the application in mind? So for the current state of time, we have to find out which kind of algorithms can run on the near-term devices, which for us basically means, as I said, we're interested in solving equations like the fluid equations, so like partial differential equations. But we do it in an, let's say, augmented way. We do it with a machine learning, in that situation, physics-informed neural networks and hyperparameter optimization. So, of course, we are using the tools for computational experiments. But as I said, the individual pieces is not enough. It's about people, it's about humans using the software, and they just don't use it in a single run only, but it is a process, it's a workflow. So they need environments for using the software in different ways of coupling. So the first, of course, is optimization. We are talking about the multi-physics, multidisciplinary. So the MD stands for multidisciplinary and the O for the optimization. The multidisciplinary can be different applications. Here in this example, it's on aeroelastics, so fluid dynamics and structural mechanics and their interaction. Their interaction for the trimming, and the optimization is a loop that runs several simulations step by step with best fitted parameters. It's here, for example, to minimize the drag, and it uses mathematical methods like being based on gradients. But for the computer science, we have to look at how to combine the different pieces such that, of course, the result is physically correct, but also that it's fast enough on the simulation side, so on using the hardware resources, but also for the people developing it, setting up the problems, and running the optimization scenarios. So we want to offer them an entire ecosystem in which you can see, for example, individual codes like the CUDA code I already mentioned for fluid dynamics, other fluid dynamics codes, structural mechanics, whatever you have in mind, the steering and control panels like for the optimization. We are also looking at offering also other fidelity methods, which we offer in our SMARTY library. And of course, that needs an architecture, a software architecture, where we have, as seen, all the individual building blocks. They need to have their interfaces and APIs to the layers above them, for the multiphysics coupling, for the optimization, but also for the layer down to the data side, because everything is in exchanging data within a simulation or on a larger run. So we offer frameworks, environments that help the users on the needless integration, also from the data perspective, from the physics perspective, but also from the data perspective. It offers unified APIs to the multidisciplinary analyzers and optimization. So it's meant to ease the work for the people, ease the setup of complex scenarios, ease also sensitivity analyzers, and it uses the improved algorithms on every level of the multidisciplinary problems in the framework demonstrated. So it's modular, it's integrated, and it maintains the parallel and algorithmic efficiency. But even with that, we are not yet done. Everything I talked about up to now was especially on the design phase, but also when the airplane is flying, we need to offer the data, make the data available. In our context, make it available cross-site as a service, the data connected to applications, because it's not just about having the data and finding it, but it's about working with the data. Our platform, STASH, I would have been happy to show you a little video, but time is running, so I have to skip the video. But of course, again, it is addressing the user, so it needs to offer front ends, visualization, tools to work with. And from there, again, I want to come to the even further tools. When talking about data, you would probably be astonished if I would not use the buzzword of AI. So we have the simulation methods, we have the AI methods, but they are no longer standalone. They are converging. So we would like to call it AI-augmented simulation. So we use it to extend the existing, the physics-based models in some kind of a mixed mode simulation and AI. And that gives us another degree of freedom to find the best trade-off between explainability, accuracy, and performance. And again, this is on the way forward when developing an airplane. But when we come to a point like certification, then we also have to be able to turn around and have the look backward from the point where we have the development, and then proving backward where the data is coming from, for example, where the provenance of the data is, to ensure for the certification authorities, in our case for EASA, that the process has been well managed and done in a proper way. So we need to have both ways of looking at the data, the forward way, the backward way. And yeah, the main purpose is to integrate every method that we have available when developing machines, when bringing them to certification, and coming back to all the different steps in there, the high fidelity simulation, the surrogate models, the data, measurement data, simulation data, everything feeding into the same process. But feeding into the same process does not mean that we want to have one single, let's say, the data grave where everything is down in, but when dealing with a process that has several stakeholders, we have the distributed functionalities between the stakeholders. Distributed functionality also means distributed data. So if everything is in the same environment, then it's easier to control, but it won't live in real life industry when we have the small and medium-sized enterprises delivering to the large scale industry. Data is the capital of the companies. So as they would not spend all their capital, their money capital in one big pot, they won't do that with the data neither. So we have to be able to deal with the distributed data, but for making it possible to prove backwards who has worked on it, where did the data come from, with which methods it has been produced, that requires the provenance, and we want to assist people also there with, for example, a tool like the provenance container. And from there, I would like to come to, I'd say, my last buzzword, drawing the entire picture. Of course, we are also talking about containerization. We offer our own HPC environment, but we also are discussing with our partners, even with our industrial partners, how to deal with peak load. And of course, we are investigating also public clouds, and we are working on methods in the digital ecosystem of the Gaia-X consortium. So with that, I think I have done a quick rush. It was a tour de force, as I announced in the beginning. I did not go in the detail at any point, but to draw the entire picture, what is needed when we want to achieve the virtual aircraft. All those pieces and building blocks are necessary. So for our institute, our goal is to do the research and the development in computer science, to develop the techniques, the methodologies, the software foundations for the description and the realization of the virtual product in all its aspects, which also includes the high fidelity and multidisciplinary simulations, which requires HPC. So that is a big focus point for us, the simulation environments and the software methods. But having said all this, we're talking about technology, but it's not just on technology, it's on people, it's on corporations. We already heard the strong collaboration, close and very fruitful collaboration between DLR and ZIH. And I would like to thank Andreas Knüpfer and Daniel Hackenberg. Daniel's where? With both your groups on the research side and on the operations side. It gives us the best performance only when it goes hand in hand. We need both. Operations need to know what research is asking for, but research also needs to know what what operations can offer. That holds in HPC operations as well as in production of aircrafts. So that's the strongest collaboration. I would really like to thank you very much for that. I would also like to thank other collaboration partners. I just mentioned some to be representative in projects like the LUFO project, so Luftfahrtforschungsprogramm funded by BMWK. where we are working together with different partners. We are collaborating also, not just me in the professorship, but in general in teaching. For example, Arthur Stück, who still is on his way back from Toulouse, and therefore he did not make it in time back to Dresden. So he teaches on probabilistic and robust design. We are working together, for example, with ELK, with Professor Gude, in projects funded by BMBF, but also by the state of Saxony, in projects like the calls on change by innovation in our region, and also with partners like IMA in educating people, supervising master theses together with Björn Andres, who I think hasn't been able to be here today. So all the partners we have form the collaboration and the basis. But of course, my special thanks goes to my colleagues in the Institute. Just some names given here, where I used your slides, who contributed to that talk, but see yourself as the representatives of all the people in the Institute who deliver ideas, software, methods, but also public relations, bringing the things that we do to the broader area. Franziska, where are you? Yeah. Thanks for you and the colleagues having been yesterday at on the show floor of the Forum Sachsen Digital, of the Future Sax collaboration. You brought the developments to Minister Dulik. And so what we want to do, what we want to achieve is start in the basic research at TU Dresden, bring it to the technology in institutions like DLR, to bring it to industry and to society in the end, and to bridge all those scales in the multi-scale approach. That's what we are considering, that's what we are working on. And with that, I also thank you, Wolfgang, and hand back to you. Thank you.
Geht es so? Ja. Thank you very much for your wonderful talk. It opens lots of questions. I'm not sure that you get dinner tonight. Let's start. Who has the first one? You know, the first one is always the most difficult one, but after that, it's running. Michael.
Yeah, thank you very much for this inspiring talk of all the methods of high-performance computing. I'm coming from the background of the big particle physics experiments, where we also use a lot, thanks to Mr. Data Dresden high-performance computing. What I found very interesting is your connection between simulation and artificial intelligence. We usually do a lot and involve programs with a high computing time. We use parallelization there quite much for this simulation, but the artificial intelligence and machine learning we use at the end for pattern recognition, for seeing what has happened, for telling data or telling a signal from background, but we never have used artificial intelligence in simulations yet, and so I was wondering how you do that.
So if you just consider the process which you just have described, the serial process, and you feed back the information into the simulation. For example, in the fluid dynamics, it's usually about turbulence modeling, and that is expensive. If you have some simulations where you have done it on a high fidelity method, highly resolved, you can feed back that into the next simulations where you can just save time. by using the understanding, the patterns, the recognition in the simulation. You can do it in physics-informed networks, which is the other way around. You do the machine learning, but you augment it with a knowledge on the PDEs, solving it for the residuals of the PDEs, things like that. So it's more like a circle. It's converging, and it won't be an either or, but it will be integrated.
Thanks a lot. Any other question? Please, Ivo.
Sabine, the million-dollar question. Can you explain how a CFD solver on a quantum computer would work?
It's more than a million, huh?
Not yet.
We have all evening long. There's 5 blackboards there.
This is a really difficult question.
But are there any first ideas, or you mentioned you want to approach it through machine learning, so I assume something like a pin on a quantum computer.
All right.
With quantum nodes.
Quantum machine learning then with the pins, yes.
Okay. Anything more than that?
Not yet.
Not yet, okay. Or you're not allowed to tell us.
There are 2 different types of quantum computers. We have the quantum annealers, which are available today, but they basically solve the traveling salesman problem. So everything that looks like a traveling salesman problem is fine on the annealers. But yeah, if you have a hammer, then everything looks like a nail, right? We are more waiting for the quantum gate, which we think might be much more general purpose. But they are not on that state.
Ursula?
Thank you, Professor Roller, for this very succinct and precise talk. Now, you have to forgive me because I'm a complete amateur, so I'm coming from a bird's eye view, and I'd like to understand how the interaction or the dependency of what you and your team is doing is on the type of data that you work with. So I understand you're putting together different components that make up, let's say, an airplane, you know, in a static condition, but also in a flight, in a dynamic condition. And so you're deeply dependent on the engineers, the physicists, and whatnot, who produce the data sources that you need to come up with your models. Is that assumption correct?
Yes and no. So on the physics side, on the application side, it's the application people who have to think in what is the meaning of the data, what can I do with the data. We can support it by software, but of course the software is not a standalone. We need to understand what they are looking for to be able to support it. So it needs the collaboration between the people from the different disciplines. And even in the application disciplines, we have people which are more the experimentalists. We have people who are more doing the simulations, and we also have to trigger the discussions between them, and we can support that by software to make it easier to hand the data from one step to the other, or make the data from the one be interpretable for the other.
Yeah, so what I want to get at is to which degree, by producing the platforms that you have been describing to us, might be an important part of a feedback loop that provides validation information for what you call the application stakeholders, so that they come with certain assumptions, theoretical assumptions about the different important components that make up a plane. And they may be wrong, they may be right. And so I'm trying to better understand where does like a reality validation come in, or how can your work, which is first of all content-free, quote unquote, if that is possible at all, nevertheless become very content-oriented by the things you're doing, by be it the AI components, or be it, of course, the simulations, of course, probably. And the second point that
I had in my head all the time is if you were speaking about online, an online use of your models. I understand that to say that the pilot or whoever it is can make use of the platform, or did I misunderstand that?
So yeah, the engineers make use of the platform, so it's not open in the internet.
No,
it's
I
not a web
understand.
portal or something like that. But it's meant to be used, of course, for the engineers developing, for example, a new airplane. Maybe I can first answer the first part of your question. We always have several steps. We have some steps which are closely coupled, where we aim for an automated process, like in those optimization loops. But what you were describing is more workflow, where we hand over things from one station to the next, and maybe back. So that is another kind of platforms, talking about workflow engines and workflow methods, where still the people, the human is in the loop.
And is there data collection going on, let's say, in the course of further developing a plane in flight mode, or that's not playing any role?
There is flight data collected, of course,
yes,
but usually the transfer of the data is only after landing. So it's not
okay.
a real-time transmission,
it's not real time.
At
Okay.
least not at the current point in time. That is also an issue on what to do where. So for which step, for the development of the next airplane, it's important to have all those data. But for that, it's not necessary to have it in real time. If you want to have something in real time, then maybe you just do it in the cockpit.
And would you influence the type of data collected, i.e. would you give feedback, so which type of sensors, where, or is that something that is just delivered to you?
Yes, that is delivered. That
Okay.
is what the engineers in the fields, in the different fields, in production it's different than in maintenance, for example. They are the ones who define which data they need. We can help them in find the best formats or in make them available. What we collect is, as I mentioned, the provenance is information on from which step to the next, but not as a large, ever-growing, but as metadata to the data, but they might stay where they are, and they do not necessarily all be collected at the same point.
So my question comes from an analogy, which may be a completely wrong analogy. So when we speak about circular economy, we have come to the insight that if the people who try to take apart certain objects and try to recycle them, it would be good to speak with the engineers who design the objects in the first place. And in an analogy, I would say it might be, the ideal that the people who, like you, who use the data, speak back to which type of data are produced.
Basically, we are not the ones to use the data. We are just the ones to deliver. It's other people. It's again the engineers.
No, but you use them to build the models and the simulations. That's what I mean.
No, also that is done by the engineers. So of course we help them, but the model. So for example, do we need fluid dynamics, to come back to that? Do we need fluid dynamics to build an aircraft? That is a decision of the engineers, not of us in the computer science. But we can help them to improve, and of course we need to have knowledge on that. In our institute we have a wide distribution. We have computer science people, but we have engineers, we have mathematicians. So it's a need to bring all that knowledge together, of course, to improve it. But it's not us to build the models.
Yes, Andreas?
So thank you for the presentation, and also, of course, thank you for having us as a part of solving your challenges. You showed nicely how you want to have all the aspects simulated that make an airplane fly and work. And I know that CFD is really complicated, and so is the structural parts and many more. but there is this trend that everything, including airplanes, is more and more software defined. So software is a part. And maybe as a general question, how much are you looking forward to simulate software as part of the airplane and then doing software for this simulation?
Probably the answer is similar to how I provided that talk. So ever more complex is easy to do, but let's start to do it step by step. So for the moment, it's about things like doing a virtual first flight in the computer, things like that.
Thank you. Yeah, Andrea, Uwe.
Yeah, so we have seen this effect of fly-by-wire being transported to other domains like drive-by-wire or trust a robot by the wire or whatever. And we will see, of course, many more autonomous systems like that. So what will happen with the virtual product airplane? What do you think? When will it be transferred to cars, to robots in factories, to our smart homes? What do you think?
There are a lot of methods to be transferred. There's always a part which is generic, and there's a part which is specific. And the more flexible the environment is, the easier it is to transfer. But it's not possible to have something which is the Eierlegende Wollmilchsau. Even for the plane, the digital twin of a plane, the digital production twin is something else than the digital maintenance twin. So even within one area, you need to have different specifications for the different purposes, but they have to be able to talk to each other to find out what is coming from where and how it is going through the pipeline or later on through the circle in the development.
Yeah, I think that's a challenge for the Dresden researchers to really do this transfer as you described, because, well, one could make Dresden to the town of virtual products. That would be great. I'm not sure that we can do that, but good luck.
Let's see. Thank you.
Yeah. Lars.
So now a question from one who is acting as the CIO of TU Dresden's and related to a more political one, let's say, that was your Gaia X slide. And now if you would have to judge what kind of impact would Gaia X have on our, let's say, research data or information infrastructures, what would be your answer on that one? As you are involved in the building of Gaia X.
So I think it will provide different facilities, different opportunities for different applications. I think the usage of the developments in academia will not be the same as in industry, because, and also in the different disciplines. You might have disciplines like, I don't know, the high energy physics, which is a community where it's easy to share everything, maybe with a restricted time until the first publication, but then afterwards you can share everything. Well, when you go to industry and you look to SMEs and the way how SMEs work together with other SMEs, but also with a large industry, they won't give everything into the same data repository, for example. But they will nevertheless use methods to exchange data or to hand over the necessary information without handing over all information. It's like when selling cigarettes to someone, you need to make sure that this person is above 18, but that does not necessarily mean that you have to deliver the entire birth date. And we will have this discussion on the data levels.
May I? Just a second one on that one. I see that and I can fully follow that. So thinking about the AI applications that you mentioned, would you see that there's a chance to have that being operated in such a federated system, or would you think that we have to go for another approach, like data trustees really providing a data lake that you can then operate on?
I don't think that the data trustees will be fully accepted, or at least not one. So probably that has to have different trustees. I think there's more work to come on the federated system. So if you look at the AI methods, currently they are mainly trained by a set of data and then applied to the next. But there is already research on first training and then retrain and improve and improve. And that is the first step. The technology has to be able to become better with a retraining, and then afterwards you can apply that in a federated environment where the first one starts to train the network and then does not hand over the data, but the trained network to the next step. But that's to come, because first that retraining needs to be reliable and stable.
Alf? You put together methods and tools to simulate your aircraft, which means that you have to take care of several orders of magnitude, yeah, from the whole plane and the turbulences down to the materials. What precision is the goal, and where are you now?
That's again different in the different steps. So when designing a new airplane, then, for example, in the aerospace institutes, they start to develop with a high-fidelity simulation to find the region, and then from that they feed the surrogate models, and then continue next steps with the surrogate models, and maybe come back to the highly resolved in the end. So the need for high compute power is increasing. It's increasing in both ways, in the sense that there is a need for those simulations that feed the entire machine, but there's also a need for, let's say, high, how to call it, a mixed capacity and capability computing. So if we, the one thing is to have the single simulation on EXA, or at least on petascale, but the other step is to have thousands or 10,000 simulations on the tera or petascale, which also is a need, and you can, it's capacity computing, but capacity that already needs a high capability if you talk about each individual run in the tera or petaflop range. Is that?
I meant more the, let's say, the physical precision, yeah, for the airplane. How far are you away from simulating the perfect airplane?
That depends on the definition of perfect. I mean, it's always the question, yeah? What is the question you want to answer with your simulation? You don't do a simulation just because it's so nice to do the simulation. You always have a question, and depending on the question, you need it highly resolved in some areas, and for others, you need the entire airplane, and of course, you need to be as resolved as possible to represent all the interactions. And depending on the interaction, the answer is a different one.
And for, let's say, for the design, current design of an airplane, is it enough, or how far are you away, or how satisfied are the engineers that want to construct an airplane?
There's the definition of an HPC machine. An HPC machine is a machine which is always one generation too small for the needs of the users. So whatever we offer, they are able to do good development with the resources that are currently available. But there's always a need for larger, and the answer to that point is different for academia than for industry. For industry, they are often, it's time to market for the product, so they are often more satisfied with a faster solution, even when losing some details, While in basic research, we're now thinking about new configurations of airplanes. There you need to have the higher resolution.
It seems that we are all eager to get to the champagne. I have one challenging question to you, which is not really related to that thing, but to the personal experience. You have had a couple of universities, you have a couple of different organizations, you headed them. Now you are at DLR and you are at our faculty. I could ask, what has changed? And I would ask, what do you want us to support you?
So what has changed is, again, the broader view. It brings together, so coming from university and then discussing with industry, strips down some of the requirements. On the other hand, it attaches new questions. It's more on the general instead of or both needs the deepness and the generality. And I think that is one of the most important needs, to support or to educate people that are able to do the research in those interdisciplinary fields on both sides, or on all the three sides, considering my math and engineering and computer science. Everybody needs to have deep enough knowledge on the other sides to find a common language.
Okay, thank you very much. I think I have to have a duty which I haven't done beforehand. I think between or behind every important person is a family. And we have 4 sitting in a row. So the mother, which joined, which has moved from quite remote, Siegen, to the place in Dresden, nearby, 2 sons, and my colleague Alexander Kionke, who is heading my Network Operations Center. So thanks a lot for supporting her, and thank you for joining her, and thank you for your work.
Thank you, Sabine. Thank you, Wolfgang. And I have the final pleasure of handing you over flowers. I will do it with the vase, so then we don't make a mess.
Thank you.
Ganz herzlichen Dank.
Thank you very much. Dankeschön.
Und alles Gute bei uns.
Dankeschön.
And now we take a group picture, and I thank you all for coming, and I hope to see you downstairs at the reception.
Dankeschön. Dankeschön. Müssen wir, ist das voll?
Sabine in die Mitte, ne?
Ich bin hier. So, wo soll ich hin?
Und natürlich mit den schönen Blumen.
Mit den, dann nehmen wir jetzt so.